Good. How do you remember, how can you remember that cations are positive ions?
Cats have paws.
Right? Yeah, cats have paws. Good. So cations is a positive ion, and an anion is just the other one, right? If it's not positive, it's negative. Okay, all right. Molecular compounds. Molecular compounds you should be able to spot from a mile away because they never have metals. They never have metals in them. Now, that's kind of, there are some exceptions to that rule, where there are certain compounds that don't have metals that are ionic compounds, but that's totally fine. So there's no metals in the name or in the formula. Molecular compounds, there's a lot of them that you would have had to memorize. Do you remember any of those compounds that you were supposed to memorize? No? Like, what's the formula for water? Oh, okay. So you remember some of them, right? Okay. Do you remember what the formula for ammonia is? NH3. Ooh, that's okay. That's all in your data booklet, right? So you can look it up. Acids. Acids always begin with, what do you think? They always begin with H, or they end with COOH. I apologize right now. I'm very sincerely sorry. I tried to teach myself a different way of writing my H's, but they always end up looking like that. I'm so sorry. Now, for some of you, that doesn't bug you because you immediately notice that that's an H, but for some of you, that's really going to bug you all semester, and there's nothing I can do about it. Okay? Bases. Bases are always, as far as you're concerned right now, okay, bases are always ionic hydroxides. What does that mean? It looks like M, just standing for metal, right? Any metal, whatever, and then OH, or MOH2, or something like that. And then elements. What do elements always look like? Just a single symbol, right? With a number maybe on it. You know what I mean? Right? An element is only one element. Now that sounds stupid, defining an element as only one element, okay? But that's what we're going to roll with right now. So for example, Fe, that's an element, right? Or S. No? Okay, sure. Si, yeah, sure. But S8, that's kind of what I was going for. Well, that's my fault. Wait, you should be able to spot these from a mile away, given the name or the formula. Now, all of these things kind of do different things in solution. They kind of do different things, and because they do different things, they behave differently. And because they behave differently, it's important for us to know a little bit about them. In Chemistry 30, there are 2 units where you are going to be asked to predict the major reaction involved. Predict the predominant reaction involved. And if you can't do major entities, you are pooped. You're totally boned. There's no way you're going to possibly be able to do this unless you know your major entities. So let's start off by talking about the ionic compounds. This is an ionic compound. And ionic compounds with high solubility, they will dissociate into ions. I don't know what Mr. Zakowski's doing right now, but you can expect a lot of that over the semester. What I'm going to do is we're just going to watch like a really boring video, like a super boring video of ionic compounds dissolving in water. Ah, no! There we go. Oh yeah, hell yeah. You can tell it's good already. Oh, what's that? What are we looking at? A water molecule. Yeah, we are. That's a salt crystal. Good. Way to narrate, Walton. Fantastic. Water molecules are polar. They have a positive end and they have a negative end, right? So we've got a more positive side and a more negative side. Now, this ionic compound is made up of positive and negative ions. It's made out of ions already. This thing is alternating negative, positive, negative, positive, negative, positive, negative, positive, right? So what's happening is this negative ion, is it able to be attracted to water in any way? Yeah, what are negatives attracted to? Positives. Does water have a positive end to it? Good. Holy, I just got choked. So the positive end of water can attract, it can dissolve, or it can surround that negative ion, okay? The positive ion, this positive ion, could it be attracted to water? It's positive, so what's positive? What are positive things attracted to? Negative. And when we look at water, water has a negative side as well. So one side of the water is attracted to the positive, one side is attracted to the negative. And so let's see what happens. Oh yeah. That's what I'm talking about. Isn't that beautiful? That's so good. Woo! Look at those ions. They are dissolved. I love it. So this is what happens. When you put a salt crystal into water, that salt crystal, that sodium chloride crystal, it will be able to dissociate. See how all the positives and negatives are being broken up? Right? That's what you should envision when we add a, thanks, Canadian Museum of Nature. All right. So that's what you should think about when you think of an ionic compound being put into water. Of course, there's two different general categories of ionic compounds, okay? So high solubility compounds will dissociate. Low solubility compounds will remain a solid. Can I get you, pretty please, to go into the Chemistry 2030 data booklet? And I would like you to go to page 6, I think. Go to page 6 for me, please. Do you remember using this chart? Yeah, you used this chart 2 years in a row now, or maybe 2 semesters in a row, something like that. You used this in grade 10, and you also used this in Chemistry 20. We're going to continue to kind of use it in Chemistry 30. So, what do I mean by high solubility compounds? Somebody tell me, where are all the high solubility compounds located in this chart? Do you remember?
Middle row.
In the middle row. Anything that's in this middle row, that's high solubility. Anything in the bottom row, that's low solubility. If you wanted to, you could totally put aqueous. It's not going to be able to let me do it because I hate my computer, but it's fine. So you could totally put aqueous there, and you could put solid down there. If you really wanted to, it doesn't matter to me. I'm going to say this probably one time and then forget to say it for the rest of the semester. You're not allowed to use your data booklets for exams. Quizzes are fine, I don't really care about quizzes, but exams, you're not allowed to use your data booklet. Is that okay? I'm going to give you a fresh data booklet, and you'll be able to highlight or whatever, and you'll be fine. So for all exams. Okay, let's take a look at the first ionic compound. This is an ionic compound. You should be able to spot this a mile away because it is cation, metal, and anion, non-metal. Any questions so far? Sodium phosphate. Let's look it up on the table. What are you looking for first? Let's look at the top, in the top row. Is there anything in the top row you can find like sodium or phosphate? Yeah, you can actually find both of them in the top row. But that's fine. Which one is really obvious to see here? Phosphate. Yeah, you look here. No, yes. Phosphate. Okay, good. So then I only care about this column now. Do you remember that? Once you've identified where your anion is, you only care about this column. Phosphate. Let's look underneath it. Do you see sodium here?
Group 1 ions.
Yeah, it's hidden. You have to know a little bit about sodium. Whenever it says group 1 ions, what does group 1 mean? Jaden.
First column.
Yeah, first column, that first family of the periodic table, right? Please keep in mind, hydrogen is not a group 1 ion. You understand that, right? Okay. Hydrogen is special. It doesn't belong to any category or any family or any group or anything like that. We're talking about just from lithium to francium. Or as the British like to call it, francium. Okay, because they hate the French. Anyways, so sodium is a group 1 element. So here we see this partnering, phosphate and sodium. So what does that mean? It's very soluble, right? Okay, so remember, in the video, when we put salt water, or when we put the salt in the water, did the salt stay together? No, it didn't. This ionic compound is going to dissociate. So, the major entities for sodium phosphate is sodium phosphate going to stay as sodium phosphate when you put it in water? No. It's going to dissociate into what two things? It's going to dissociate into sodium, and it's going to be aqueous, right? It's dissolved in water, so it kind of has to be aqueous. Also, it's going to turn into phosphate. And then what else? What else do you have in your solution? You added the sodium phosphate, but what did you add it to? Water. So in your mixture, there are three things. There's three things in this solution now. There's sodium, there's phosphate, and there's water. Now, I need you to understand, I have made the gravest of grave errors. I've made the worst error you could possibly make in Chemistry 30. What error did I make? No, don't say it out loud. I'm just going to give you 10 seconds to think about it. What error here did I make? And then when you think you got it, put up your hand. Abby. What? I forgot the charges on the sodium and the phosphate. Are these ions? Yes, they are ions. They're ions because they were in an ionic compound. Would you agree with that? And ions, I need you to write this at the very top of the slide or top of the page or wherever, right? Ions have charges. What did I do? By writing sodium with no charge, instead of an ion, what am I telling you, accidentally telling you that this is? It's an atom, right? and this atom would be its element. Now, there's a huge difference. There's a humongous difference between sodium atoms and sodium ions. If you ate a little cube of sodium atoms, right, your mouth would explode. That's no good for anybody. But if you ate, a little cube of sodium ions, hell, you've probably done that, right? You probably put a sugar or a salt cube in your mouth and totally regretted it because it tasted awful. But I mean, you've done it and it didn't kill you. So these ions, I need you to understand there's a world of difference. That is the major entities in solution. Let's look for MnO2 solid. I put a crystal of MnO2 into some water. Now, is it high solubility or low solubility? What do you think? The problem is, I don't see it on here at all. I don't see manganese, and I don't see oxide on here at all. I want to be very clear. Most oxides, not all of them, most oxides are not soluble. So MnO2, this won't dissolve. Well, if I put a cube into water and it doesn't dissolve, what state of matter did it remain? What state of matter is it going to still be solid? So the major entities is MnO2, solid, and water. Okay, let's keep going. Let's burn through this. NH42CO3. What two ions are in here? What's that first ion? Ammonium, right? And what's CO3? It's carbonate, right? So you're looking for either ammonium or carbonate. Do you find either ammonium or carbonate? Yeah, I find both of them, right? So I can see carbonate here, and carbonate and ammonium is very soluble. Or you could have done it the other way. Ammonium and carbonate's not down here, so it's still very soluble. Either way you look at it, it's still very soluble. Okay, so this thing will dissolve. It will dissolve. It's ionic, it'll split up, right? So what's it going to split up into? Is ammonium carbonate, when you put it in water, is it going to stay as ammonium carbonate? It's going to split up into ammonium ions and carbonate ions. So we get ammonium ions, separately we get carbonate ions, and then what do we always have? We always have a water. Good. Do the last two for me. It should take you like 30 seconds. Look for lead iodide and lead iodide. Okay, let's take a look at this. We have lead iodide and we have lead iodide. Okay.
One's lead 2, one's lead 4.
One is lead 2+ and one is lead 4+, right? So let's do the first one, let's do the top one. Lead 2+ iodide. I'm going to look for iodide, and I'm going to look down here, and I see lead 2+. So what does that mean? It's not very soluble, so it's going to be solid. Good. PBI2 solid and water. I want to be very clear. I'm listing things. It's almost like we're grocery shopping right now. I'm listing all the things that are available, okay? So I'm saying lead 2 iodide solid is in your mixture, and water is also in your mixture. I want to be very clear. You are not, when you're writing major entities or listing major entities, you are not going lead 2 iodide plus water. Why? Why are you not doing this? What is this telling you? It's a chemical reaction, right? This thing plus this thing are reacting together, so you cannot write that. Do you know what I mean? You're just listing out things. Okay, lead 4 iodide. I look for iodide and I look for lead 4. Do you see lead 4 down here? Sure don't. What does that mean? It's under the category most, and it is very soluble. Tricksy little hobbits as we are. Here we go. So this thing splits up into lead 4+ and iodide and water, liquid. Good. Okay. So that's ionic compounds in a nutshell, right? If it's high solubility, you can split it up. If it's low solubility, you don't split it up and it just stays solid. Any questions about that? Nope.
Wait, sorry, could you go back and, sorry, the last one again? Why is it soluble? Sorry.
It is soluble because when I look at it, it's this compound, Isaac, is made out of iodide ions.
Oh, because the lead has a different charge.
And the lead 4, and I don't see lead 4.
Okay.
Yeah.
Sorry about that.
No, it's all good. That's a fantastic question. Okay, less motor. Here we go. Molecular compounds are highly soluble. That are highly soluble will become aqueous. If there's a molecular compound that has high solubility, it'll be aqueous. While molecular compounds with low solubility will remain whatever state they started as. Hopefully that makes sense. The best way to understand is just by doing, so that's what we're going to do. We're going to do it. Hint, if something can hydrogen bond, it can dissolve. Why? If a chemical has the ability to hydrogen bond, like, for example, I hope I'm tall enough to take this off the thing. Good, I am. No, I can't often say that, but that's fine. So, this compound, it has OH, 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 OH. Because it has OHs everywhere, this is a molecular compound. I don't see any metals in here. It's totally made up of nonmetals, okay? So when I put this in water, it cannot split up. Molecular compounds don't split up because they're not made out of ions, okay? They're all covalently bonded together. These covalent bonds are too strong for water to rip them apart most of the time. So because this has OHs, what can it do between other molecules? Do you remember? It can hydrogen bond. Do you remember anything about hydrogen bonding? No? It's the strongest intermolecular force, right? Hydrogen bonding is when you have something with an OH, right? Or something with an NH or FH. And so what this thing can do now, because this thing has an OH, and what else has an OH? Water does, right? So water can hydrogen bond to that compound. They can be really attracted, and so this thing can be dissolved. Do you kind of remember that from Chemistry 20? A little bit. Okay. So if it can hydrogen bond, then it will be soluble. Let's look at this first thing. Do you see any metals in here? No, I don't see any metals. So it's for the most part not an ionic compound. It's molecular, right? Now, does anybody remember the name of this thing? Nobody remembers the name of this thing? CH3OH? It begins with the prefix that stands for one carbon, which is meth. This is meth, and then anything that ends in an OH is all. So what is this? Methanol. This is methanol. I have a big old bin of methanol here, okay? Do not drink this. Super duper toxic, will make you go blind, okay? Probably most of you don't want that. So I'm going to take methanol. This is 99% methanol, so it's basically pure methanol. And I'm going to take a beaker of water, you know what I mean? Just tap, whatever, it's all good. Water. And so, oh man, are you ready? You ready for this? You ready? Watch me add the methanol to the water. Did it dissolve?
Yes.
Did it dissolve? It looks like a little bit airy. It looks like there's some air bubbles in there, but I don't see two layers. I do not see two layers. So these two layers, they did dissolve each other. They're miscible, okay? So methanol, because it's got an OH group, it can be really attracted to water. And if two things are really attracted, then they'll mix really well. Does that kind of make sense? So is this going to stay as a liquid, or is it going to become aqueous? When I put this in water, it's going to become aqueous, right? I know it's the first day. Nobody wants to say anything. That's totally fine. So this is going to be, I don't have room to write it, but that's fine. CH3OH, aqueous, comma, H2O, liquid. Those are the major entities in solution. Let's look at this, C3H8 gas. Can this thing, does it have any OH, NH, or FH groups on it? No! Can this thing be attracted to water? No. So we will leave it exactly the way it is. Ah. What that means, when I bubble propane through water, you get propane bubbles and water. That's all you get. There's no significant mixing or dissolving going on. What about this? What about NH3? Do you think NH3 will dissolve in water? Yeah, it's got an NH group, right? And that NH group can be attracted to water. So instead of saying NH3 gas, what will we say? Good. It's aqueous. And then the very last thing, C12H22O11. Do you think this thing will be able to dissolve in water? It's hard to see because there's no OHs. Do you agree? There's not very many OHs. But this is basically the same thing as this. Were there OHs on this thing? Yeah. This is a sugar. And sugars have OH groups on them, so they will dissolve. C12H22O11, aqueous, and water. Perfect. Good, I know this is boring. I get that this is boring. I totally am very aware that this is boring. But this is fundamental to our understanding of the next 2 units. So we have to go over it. I promise you we will do something else tomorrow. Okay, are we kind of okay with molecular compounds? Yeah, Carlo. You gotta go, yeah. Did any of these split up? Did any of these molecular compounds split into 2 things and separate? No, it's because they're all covalently bonded together, right? And covalent bonds aren't broken by water. Okay, acids. I don't know if you remember, but there's two different types of acids out there. I mean, there's lots of different types of acids, but there's, in general, there's two different types of acids, okay? Do you remember the chart? The chart that lists all the acids on pages 8 and 9? Do you remember where the strong acids and the weak acids are on your table? Yeah, where are the strong acids? Up at the top, right? All the strong acids are these 6 strong acids up here. Now, if you wanted to, you could label them as strong acids. Again, because if it helps you understand, then that's totally fine, okay? But just keep in mind, you're not going to have this writing when you go to do your exams. So these top 6 are strong acids. The bottom, however many, I'm not going to count them, they're all weak acids. What's the difference between a strong and a weak acid? Jaden.
They break up too when they're put in the water.
Yeah. So when I have a strong acid, okay, here's going to be my strong acid. So it's going to be positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, 2 positive. Okay, here. So here's our acids. And I'm going to put our acids into water. Now, as soon as I put a drop of this acid into water, if this is a strong acid, the hydrogen separates 100%. 100% of the time. That's what a strong acid is. It's strong because it reacts strongly with water. Skylar, sorry.
Don't the H ions turn into hydronium ions?
They totally do. But I don't have a good model for that right now. So we just have to simplify everything. Is that okay? Yeah, perfect. That's a fantastic question. So what's going to happen is all these H's, they find the nearest water and they suck onto water, right? And they turn into H3O+. What the hell is H3O+? Hydronium, right? I don't know, do you remember? Is it all flooding back to you now? Is some of it flooding back to you? Okay, all right. So that's a strong acid. A strong acid ionizes 100%. What's a weak acid? Jaden?
No, it's an acid that doesn't ionize 100%.
A strong acid is an acid that ionizes 100%. Did you see what he did there? It was the oldest trick in the book. He was like, well, if a strong acid ionizes 100%, he said a weak acid doesn't ionize 100%. And that's exactly what it is, right? So when I put this weak acid, think of any weak acid, I don't know, HF. Is that okay? You see HF, hydrofluoric acid. Is it strong or is it weak? It's weak. It's below hydronium, right? So what that means, when I put a drop of HF, when I put some HF into water, this is what happens. Oh man, that didn't work very well. Is there a big difference between this and the previous example? Right? Strong acids, when I put hydrochloric acid in water, does it stay as hydrochloric acid? Look at hydrochloric acid. Where is it on your table? Is it strong or is it weak? Hydrochloric acid. Nobody wants to say it. It's okay. You're all quiet and you're all composed right now. It's strong, right? Hydrochloric acid is strong. So does hydrochloric acid stay as hydrochloric acid? Is there any HCl left in your water at all? No. When somebody sells you a bottle, this is a bottle of very concentrated hydrochloric acid. That's why I'm shaking it around so much, okay? This is a bottle of very concentrated hydrochloric acid. There is, I want to be very clear, there is no HCl in this bottle at all. There's no HCl. They created this solution by dissolving HCl in water. But what do we actually have? HCl turns completely into hydronium and chloride. Is that okay? Turns completely into, and we'll write that down, okay? We'll write that down. So HCl is our typical strong acid. What happens, because I wrote a plus, immediately, what do you know we're talking about now? A chemical reaction, right? We're not listing anything anymore. We're writing a chemical reaction. Now, we will list something later, but right now we're talking about a reaction. HCl reacts 100% with water. Oh, that's the wrong set of arrows. 100% to make H3O plus and Cl minus. Because strong acids ionize 100% into hydronium and whatever their conjugate base is. It's okay if you don't know those terms. It's okay. We'll go over them. We will slowly get used to this. It's okay. Is there any HCl left over? Like when I look, if I were to take a super high-powered microscope and look at the water, is there any HCl left in that water? No. 100% of it has turned into hydronium and chloride. So when I go to list the major entities, what's in the water? Is there any HCl left? No. There's H3O though, right? What else is there in there? Hydronium, there's chloride, and there's water. 100% of it split up. It split up into hydronium ions and chloride ions. Is that the same thing for HF? No. Weak acids, anything below hydronium, like HF, they will react with water still, but we're going to say less than, way less than, like way less than 50%. Sometimes 1%, sometimes 0.0001%, like way less than 50%. Some of it will still react, yeah. Some of it will still react, but most of it won't. So what does that mean? What's the major entity in here? Did most of it split up into hydronium and fluoride? Or did most of it stay as HF and water? Most of it stayed as HF, right? So when I go to list the major entities, I'm going to say HF and water. Is there a little bit of hydronium in the solution? Yes. But what we care about is what is most of the stuff in there, right? It's the major entity. That's what we care about. So what I want you to do is I want you to do the next two. Just list them. You don't have to write any equations, but just tell me what's in the water. If it's a strong acid, it'll make hydronium. If it's a weak acid, it won't make very much hydronium. Yes? Just try it. And if you mess up, that's okay. It's okay to make mistakes. give you 10 seconds to finish up, and then we're going to write what I believe to be the correct answer. I think, does anybody know when class ends? I think it's 11:33. Pretty sure. We've got 12 minutes left. We can do this. I have faith in you. We can do this. Okay. Acetic acid, is it strong or is it a weak acid? It's a weak acid, so you just leave it. Just leave it the same. It dissolves in water, right? It dissolves in water, but it doesn't split up, okay? For the most part, it doesn't split up. Now, H2SO4, is that strong or is it weak? Oh, it's strong. So what's it going to make?
HSO4 negative.
Ooh, it's going to make, it's not going to make the sulfate ion, right? It's going to make a hydrogen sulfate ion. So H2SO4, it will split up into ammonium, it will split up into hydronium and whatever this thing is, HSO4 minus. So the hydrogen sulfate ion. And water. Good? Okay. This is a little bit contentious. Now you're just going to have to trust me when I say this. As far as you're concerned, all strong bases are ionic hydroxides. What that means is it's a metal with OHs attached to it. They will dissociate 100%. I need you to just accept that strong bases have hydroxide at the end. All of these have hydroxide and they will all dissociate. You just have to assume they dissociate 100%. So KOH, potassium hydroxide, when I put it into water, is it going to stay as potassium hydroxide? No, it's a strong base. It's going to split up into potassium ions and hydroxide ions. Calcium hydroxide. Because calcium hydroxide is a strong base, when you put calcium hydroxide into water, it will dissociate into calcium ions and hydroxide ions. And then finally, sodium hydroxide, is it going to stay as sodium hydroxide? No. It's going to split up into sodium ions and hydroxide ions. And we will make sure that we get used to all of these sufficiently over the next little while. Is that okay? Bases are pretty easy. Bases you just dissociate. Just always dissociate them. Ooh, elements. Ooh. Elements should be the easiest, but actually often people find them the hardest. And I've never quite understood why. I think it's because a lot of people are still confused about the idea between atoms and ions. Every single one of these is made up of atoms. How do I know that they're made up of atoms and not ions?
There's no positive or negative.
There's no cation, anion. There's no positive negative deal going on, right? There's no metal non-metal thing. So if there's two nitrogens here, right? If these two nitrogens are bound together, then they can't both be negative. They can't both be positive. They have to be neutral. Does that make sense? For two nitrogens to be bound together, they have to both be neutral. Hopefully, that's okay. So Elements cannot hydrogen bond. They are never polar, so they will never dissolve in water to any appreciable extent, okay? Now, I want to be very clear. When I look at oxygen, is there oxygen dissolved in water almost all the time? Yes, you know that. You know that because what lives in water? Fish, and fish need oxygen to survive, okay? So yes, there is oxygen dissolved in water, but what I mean by that is that the oxygen doesn't dissolve, to any really appreciable extent. 99% of the oxygen that's in contact with the water is because it's in the air, right? Not dissolved in the water. So the state of the element doesn't change. So when I bubble, if I bubble nitrogen gas through water, are the bubbles going to disappear and they're just going to get sucked up into the water? No, they'll bubble and they'll rise to the top and then they'll go bloop and then that's it, right? So nitrogen gas stays as nitrogen gas and water. Phosphorus. When I throw a chunk of phosphorus into the water, do you think it's going to dissolve? It's an element, keep in mind. Elements do not dissolve to any appreciable extent. So I'm going to get P4 as a solid still and water. Now, I'm not saying they can't react with each other, right? So I'm just saying that doesn't happen. I feel like you're all bored and I need to do a demonstration for you right now. I'm going to prove to you that one of these is true. Is that okay? Here I've got water, no big surprise, whatever, it's basically just water. And here I've got a chunk of aluminum, and you know it's aluminum because it got tattooed with the letters Al, okay? So perfect, it's aluminum. We're just going to have to trust that it's aluminum. What's going to happen when I put this chunk of aluminum in the water? What do you think? Oh. Oh. All right. Womp womp. So have I proved to you sufficiently that the aluminum doesn't dissolve, right? It just stays as aluminum solid, and we also have water. Would you agree, in this mixture, I have aluminum and I have water? Yes, good talk. Thank you. Jaden.
But then how does it work? If you take sodium and put it in water, it blows up.
Yeah, so it'll stay as sodium, and we'll talk about this in the redox unit when we talk about oxidation and reduction. The sodium stays as sodium. It doesn't dissolve. But what it does is it chemically reacts with the water. So when I put the sodium in water, it'll stay as sodium. It won't dissolve. It won't split up or anything like that. But the moment I put it in contact with the water, it will react with each other. And we want to be able to predict that reaction when we get to that part of the unit. But that's a great question. Oxygen doesn't dissolve. It does a little bit, a tiny little bit. I need you to understand that, like a little tiny bit. But most of it doesn't. And then iron, if I threw a chunk of iron in the water, do you think there'd still be a chunk of iron inside the water? Yeah. Man, we got 3 minutes. 3 minutes to gaze at the glory of this chart. Bow down to the graphic organizer that may make your life simpler. Maybe it won't. I don't know. Do you see how this is organized? What are the 5 compounds, or what are the 5 substances you need to be able to spot from a mile away? Ionic substances, molecular substances, acids, bases, and elements. Are we good? Ionic substances, if they're high solubility, you dissociate them, split them up. If they're low solubility, leave them alone. What do you notice about almost every single one of these? Either you split it up, right, or you leave it alone. That's kind of basically the idea behind it. Acids react with water, produce hydronium, or you leave it alone. Elements, leave it alone. Molecular compounds, leave it alone, or it's soluble. So this will help you, this will hopefully help you What are the only substances that can really split up? What are the only substances that can make like two different things? When I look at this,
Ionics and strong acids.
high solubility ionic compounds and strong acids, right? They all kind of split up. Those are really the only ones. We got 90 seconds left, okay? So I've got some practice for you. All I want you to, the only thing I want you to do is I want you to try and go through here and identify these as either ionic, an element, molecular, acid, or base. That's what I want you to do. I just want you to, I don't even want you to finish it. You can finish it if you want. That's totally fine. But I just want you to identify them as ionic, molecular, acid, base, that kind of thing. So, and because there's like 10 seconds left, you can finish that up. But also, have a good day. I'll see you tomorrow. We'll actually start chemistry 30 tomorrow.